And for the very last topic that we're going to cover in this class, we need to take a look at different kinds of columns, because we do have different columns that obviously aren't pinned at both ends. So we have something like this. So these columns that are supporting the water tank, well, they're not pinned at both ends, so they are pinned at the bottom. So they're nice and pinned at the bottom, but they're free at the top. There's nothing holding them there. And we still need to be able to figure out what that critical load is, but we can't do that using the equation that we have. So in this case, like I said, it's fixed at the bottom. It's not even pinned. It's completely fixed at the bottom, and it's free at the top. That is a lot different than having a column where we've got a pinned condition, because the pinned condition is going to allow you to rotate a little bit, rotate freely. A fixed column's not. Fixed at the bottom is going to be, there is going to be no rotation. So unlike last time, we have to use a different equation in the elastic curve. And once again, since we did not completely cover the math of that, if we just kind of jump right to the end, and once again, I know you're all disappointed by this because we're not doing the hardcore math, we're going to end up with a slightly different differential equation. And it's this part here. It's no longer a zero equation. It's a non-homogeneous differential equation, which gives us a different kind of harmonic. And so we have a different solution. And once again, we go through the same thing, and we take a look at things, and we end up with a different critical load. Now, what ends up happening as you take a look at this is you're going to end up getting a critical load. It's going to be in roughly the same form of Euler's equation. There's going to be a slight difference. And that difference, which right now we're just going to call K, is we're going to get some value in there that's going to modify the length of the problem. Everything else will be the same. So in this case, where I have it fixed at one end and free at the other, K ends up being 2. And so a column that's fixed, what's called fixed and free, is going to work just the same as a column that's pinned at both ends but twice as long. And so what we end up calling this is we call this the effective length. So LE is the effective length. Now, what we could do is we could solve this differential equation over here every single time and figure out what the equation is going to be. But that's not very practical because we have a couple of just set types of columns that keep coming up again. And so this is where the effective length becomes more usable, because everything is going to end up in this form with just that K. So pinned at both ends is just 1. So here, this is a very important picture, and this is showing the 4 most common kinds. So if it's pinned at both ends, K is 1. And so once again, let's just write this over again. My critical load is going to be pi squared EI over KL squared, or the length equivalent squared, where our length equivalent is going to be K times that length. So in this case, K is 1. If it's pinned at one end and fixed at the other, so it's able to freely spin here, but it can't fit here, its effective length is going to be 0.7. So what does that mean? Well, it means actually nothing really is going on here. From here to there, it's acting like a column that's pinned at both ends. So it just takes, in this case of fixed and pinned, it takes that 0.3 length, and it takes that much length for it to act like a pinned connection. So if you've got it fixed at both ends, it's a half. So once again, things in here kind of can twist and whatnot, and it starts to buckle between those 2 points. And then fixed and free works just like a column that is twice as long. And this is the only difference in the Euler equation. So the other one that I gave you, if you just take it and replace L with LE, and all the problems solve the exact same. this, once again, only applies when the critical stress is less than the yield stress. So you are going to need to calculate out that yield stress every time. Excuse me, you're going to have to calculate out that critical stress every time and compare it to the yield stress. Because if we end up in a situation where the critical stress is greater than the yield stress, the material fails before the column can buckle. And once again, that's a very, very important distinction.